Good afternoon, everyone. We will talk about AR-based BIM visualization by Microsoft HoloLens.
For part 1, I will introduce the background on the need for the AR-based BIM visualization. The construction industry has experienced significant evolutions with BIM, enabling collaborative project planning, design, and management through digital models. However, the reliance on traditional 2D scripts in BIM systems restricted spatial understanding and visualization, potentially leading to errors due to the discrepancies between digital models and physical sites. While BIM software can represent structures in 3D, the limitations of flat screens impede immersive depth and interactive capabilities crucial for spatial perception, promoting a demand for more advanced 3D visualization tools. So for 3D visualization challenges, there's a need for advanced visualization tools. The demands more sophisticated tools for richer, intuitive 3D experiences call for solutions that enhance spatial perception and improve decision making. And there's a goals of enhanced visualization to bridge the gap between digital models and real-world understanding, minimizing errors during construction process. So 3D representation challenges. While BIM software can create 3D models, the flat screen limits immersion and interactivity. The incorporation of AR in BIM workflow offers opportunities for improved spatial comprehension, decision support, and enhanced collaboration, ultimately leading to a more accurate and efficient construction process. Real-time examination of design, issue identification, and collaborative problem-solving in a shared interactive space streamline decision-making, cut reward cost, and boost efficiency without sacrificing accuracy, making AI integration a suitable choice for the construction sector. Part 2, Introduction to the 3D visualization method and Microsoft HoloLens. 3D visualization in construction enhances BIM efficiency. All the limitations of traditional method is conventional 3D models are displayed on 2D screen, limiting depth perception. So it needs further immersive tools, such as development of interactive tools to improve spatial comprehension and allow real-time update. In the domain of 3D visualization, traditional methods on 3D screen hinder users' ability to grasp depth and spatial relationship accuracy. Immersive 3D visualization tools and AI applications have been developed to address this limitation, providing stakeholders with intuitive ways to explore complex construction models and understanding design thoroughly. Microsoft HoloLens, an AR device, revolutionized 3D visualization by overlaying a holographic model on real-world spaces, offering mixed reality experiences that enable interactive engagement with BIM data. Equipped with deep cameras and sensors, HoloLens accurately maps the environment, allowing users to interact with BIM elements through gestures, voice recognition, and gaze tracking, making it accessible to construction professions. For part 3, our experience using Microsoft HoloLens. Practical experience with HoloLens have showcased its value in enhancing spatial visualization and collaboration in construction projects. By superposing 3D BIM's model onto reality, HoloLens creates an engaging environment that efficiently conveys scale, depth, and spatial relationships. The device's user-friendly interface, coupled with gesture and gaze recognition, facilitates seamless navigation and manipulation of BIM elements, enhancing the overall use experience. While AR technology offers numerous benefits, challenges like the learning curve for new users and limitations in viewing large models emphasize the importance of user training and familiarity with the device. Overcoming these challenges is crucial to fully leverage HoloLens capabilities in construction projects, paving the way for immersive, interactive environments that bridge the gap between digital design and physical reality.
From application 1 to 3, we can see that many quantifying data are obtained in our experiments, such as 25% reduction in the time and 10% increase in the detection of discrepancies, which we will elaborate in Part 5. Then let me introduce Part 4, potential application areas of Microsoft HoloLens for the extended use of BIM. In this part, we explored 5 typical applications. As for the first 3 applications, we conducted 3 experiments in our 3 trials, in which we obtained relevant data to support the applications of HoloLens. As for remaining 2 applications, we collected corresponding literature to support the applications. As for application 4, using HoloLens allows workers to identify the precise position and orientation of each component within the overall context of the building. Such precise guidance helps minimize errors, decrease rework, and enhance overall efficiency. As for application 5, by overlaying safety data such as hazard zones or equipment locations onto the real-world perspective, workers can gain better situational awareness, and the workplace accident risk will be lower. In Part 5, investigation of practical scenarios and feasibility of Microsoft HoloLens use, I will explain the processes of our 3 experiments in detail to assess the feasibility. In Experiment 1, a BIM model of a small office building section was prepared. 3 team members respectively served as architect, structural engineer, and contractor to have a briefing training session to discuss design review processes. Then, we were positioned around a large table in a well-lit conference room at the industrial center. The HoloLens devices were set up, and the BIM model was loaded onto each device. Each one was assigned a specific floor plan to review. In data collection, the review was timed using a stopwatch, and we used the HoloLens annotation tools to mark clashes. In post-trial analysis, a comparison was made with review time and clashes identified using traditional 2D drawings. This experiment simulated a real-world construction site using a constructed physical model and a corresponding BIM model. Team members used HoloLens to overlay the BIM onto the physical model, comparing the physical process to the design. The goal was to measure improvements in discrepancy detection. Processes similar to last experiment, there are preparation work, task process, data collection, and post-trial analysis to explain the experiment process, which finally achieved a 10% increase in the early detection of discrepancies. This experiment evaluated HoloLens' impact on stakeholder understanding. To simulate the stakeholders, one with construction experiences but one without, were selected to represent typical client profiles. The stakeholders independently explored the model using HoloLens in a quiet room, with team members available for immediate questions. After the trial, each stakeholder completed a questionnaire encompassing questions on understanding, ease of use, and visual clarity, alongside open-ended questions for detailed feedback. From above 3 experiments, we obtained corresponding results which quantify the effectiveness of using HoloLens in typical applications, as well as their feasibility. What's more, there are some benefits and challenges exposed in our tales, which will be elaborated in later parts.
For part 6, we will talk about the benefits and challenges. And there are many advantages, such as the first is the enhanced spatial understanding. It provides an immersive 3D visualization of BIM models, allowing stakeholders to walk through digital models. And the second one is collaborative design review. The multiple stakeholders can interact with the same 3D model and reducing the design review time. And the last is the real-time monitoring, like overlaying BIM data on social structures, and it can reduce the discrepancies between the models and real-world structures. Traditional 2D BIM systems can constrain spatial perception, leading to design misinterpretations. The HoloLens provides a 3D overlay that helps users comprehend the spatial configurations better. This reduces the potential for design errors. HoloLens facilitates the real-time collaboration by allowing multiple stakeholders to interact with the 3D model together in the physical environment. This reduces the time needed for design reviews and enhances the decision-making processes. For the real-time monitoring and by overlaying BIM data onto physical structures, HoloLens helps identify discrepancies early on. This proactive monitoring reduces the costly rework and aligns construction with digital models. For the challenges of implementing HoloLens, the first is the narrow field of view. Users may need to reposition or zoom in frequently to view the large BIM models, interrupting the workflow. And the second is the interoperability issues, such as exporting and importing the BIM data to and from. HoloLens often requires third-party plugins demanding technical resources. And the third is the learning curve. The gesture-based controls require training. Initial sessions show that team members need practice with AR interactions. For the detailed information of the challenges, the first is about a narrow field of view. Users must frequently adjust their position in or zoom out, and reducing the workflow fluidity in complex projects. And exporting and optimizing the models for HoloLens use demands technical resources, increasing the project setup time. And the last is about initial sessions indicate a need for further familiarization with these interactions among team members. It slows the adoption. The last part is about the suggestions for better use of AR-based BIM visualization. There are many suggestions. For the first is about workflow optimization. We should adapt the workflows to include AR early in design for conflict resolution. And the second is about improve the interoperability. It should use open source formats and standardize the data models for seamless HoloLens integration. And the third is about advanced training programs. It should conduct the scenario-based workshops to familiarize users with gesture controls. And the last is about structure feedback mechanisms. We should collect and analyze the feedback to refine the AR/BIM workflows. Thank you for your time, and here is our reference list.